Welcome to this explainer. If you've been building with large language models, you've definitely used or at least heard of LangChain. But there's a massive architectural shift happening right now. We're moving from simple, straightforward chains to complex, autonomous graphs, and LangGraph is leading the charge. Today, we're breaking down exactly what these frameworks do, how they differ, and honestly, how they're going to completely change the way you build and scale your AI agents. Let's get into it.
All right, here's the game plan for today's explainer. We're going to cover linear chains versus stateful graphs, look at LangChain as the assembly line, and LangGraph as the autonomous loop. Then we'll get into some advanced agent design patterns and wrap up with how this all impacts scaling your AI strategy.
But before we get into the tech, we got to talk about the elephant in the room. Why do AI prototypes fail so often in production? You know the pain point? Stringing together a prompt and a model is surprisingly easy, right? It looks like absolute magic in the dev environment. But pushing that magic to production, trying to keep it from getting stuck in endless loops, losing its memory, or just straight up crashing when it hits a weird error, that is incredibly hard. And it really all comes down to the underlying architecture we're using. So the crucial thing to understand here is this foundational architectural difference. Early LLM apps relied on a DAG, a directed acyclic graph. Fancy term, but it basically just means a strictly one-way flow of data. Data goes in, data goes out, no loops, period. But real-world advanced agents, they don't think in straight lines. They need a cyclic graph. They absolutely need an execution model that supports looping back to retry tasks, branching off to use different tools, and retaining state or memory along the way.
Which brings us to Section 1, linear chains versus stateful graphs.
When you put them side by side, the division is pretty stark. LangChain's linear chains are deterministic. The data flows strictly forward. And hey, that's excellent for simple RAG pipelines, where you just grab some docs and answer a question. But LangGraph, it completely changes the game. Data flows in cycles and loops, and it treats stateful execution as a first-class citizen. That is exactly what you need for complex, multi-agent coordination, where the AI is actually operating autonomously.
All right, Section 2. Let's look closer at LangChain, the assembly line.
Think of the LangChain expression language, or LCell, as a highly efficient factory assembly line. It flows cleanly. Step 1. Your prompt template sends the parameterized instructions. Step 2, the LLM processes it and generates a response. Step 3, your output parser kicks in and extracts that response into structured data, like a JSON object. It's modular, it's composable, and it is absolutely perfect for knocking out tasks in a straight, uninterrupted sequence.
But here's the catch. As your AI apps get more ambitious, that one-way assembly line hits a hard ceiling. What if the LLM messes up and needs to retry a failed task? Or what if you need to branch off in a totally different direction based on an intermediate result? And this is a big one for enterprise apps. What if you need to pause and wait for a human to approve an action before the AI goes off and buys a stock or sends an email? A linear chain just isn't built to maintain state across long workflows like that. And that breaking point leads us to Section 3, LangGraph and the autonomous loop. Take a look at this tiny snippet of code. It might look simple, but it unlocks incredible power. It shows how LangGraph can dynamically inspect the AI's current state, its active memory, and then use that state transition to conditionally route execution. So instead of a hard-coded sequence, the graph uses a routing function to decide on the fly, hey, did the LLM just ask to use a search tool? Cool, route to the tool node. If no, route to the end. It's dynamic decision-making baked right into the architecture.
And this whole system is built on 3 core pillars. First up, nodes. These are just Python functions doing the actual discrete work, like calling the LLM or executing a tool. Second, edges. Think of these as your traffic cops, routing the execution flow normally or conditionally. And finally, the star of the show, state. This is a typed dictionary holding all that shared memory that gets passed around, read by, and updated by every single node in the graph.
Because of this stateful loop architecture, you instantly unlock some serious superpowers. Checkpointers give you instant resumability by saving the state after every node execution. You get built-in human-in-the-loop oversight, meaning the graph can literally pause, wait for a human to review the state, and pick right back up. You even get time travel debugging. You can literally replay a historical state to see exactly where your agent went off the rails. Plus, true fault tolerance. If a node fails, you recover from the checkpoint without restarting the whole process.
Moving on to Section 4, advanced agent design patterns. Now let's ground this theory in reality. Check out the corrective RAG pattern. The absolute best part of this is that the agent double-checks its own homework. In standard RAG, if the retrieved docs are garbage, the AI just hallucinates an answer.
But with a cyclic graph, the LLM evaluates the context first. If it's poor, it reformulates the query and automatically triggers a fallback web search. It keeps looping until it finds high-quality context before generating the final answer. It's a game changer.
And then we have the reflection agent pattern. This is where graph loops let an AI critique and iteratively refine its own work. Step 1, a generator agent produces an initial output, let's say a block of code. Step 2, a totally separate critic agent evaluates it. Step 3, the generator takes that feedback and refines the code. This loop keeps going until a quality threshold is met. You just cannot build this effectively without a cyclic graph.
Let's zoom out a bit for Section 5, Scaling Your AI Strategy.
When you look at the business impact, the trade-off between these frameworks is pretty clear. LangChain optimizes for speed. It's going to speed up your rapid prototyping and let you quickly deploy simple Q&A features with relatively low development complexity. LangGraph, though, that is your heavy-duty production engine. It brings high fault tolerance and scales beautifully across multi-agent systems, though you are taking on medium to high development complexity to get there.
So, knowing exactly when to reach for each tool comes down to your project's demands. Stick with LangChain when you have linear prompt to parser flows, simple RAG pipelines, and deterministic workflows that do not require looping. But the very second you need autonomous tool-using agents, human oversight approval gates, or complex plan and execute workflows, that is exactly when you must switch over to LangGraph.
And I think this perfectly sums up the biggest takeaway from this explainer. LangChain and LangGraph are not competing frameworks. You don't have to rip and replace. They're literally designed to work together. You just build your custom prompts, tool integrations, and basic chains in LangChain, and as your app grows, you embed those chains as individual nodes right into the stateful routing architecture of LangGraph.
I'm going to leave you with this provocative thought to consider for your own development projects. Take a hard look at the AI systems you're building right now. Are they stuck blindly moving forward on an assembly line, failing the second things get complicated? Or are you ready to evolve them into autonomous graphs that can actually think, loop, reflect, and recover? Understanding this shift is absolutely crucial for building the next generation of intelligent, reliable AI applications. Thanks for joining me on this explainer, and happy building!